Good evening everyone. See, the topic of my presentation is space charges in dielectrics pulsed electroacoustic measurement system. So this is actually part of the work of my PhD students who are about to submit their thesis. I am from Indian Institute of Technology, Ropar, which is near to Chandkheda in Punjab, 45 kilometers from Chandkheda in Punjab. So this is the outline of the presentation: introduction, cable insulation, objectives of the research and work plan, modeling and simulation of the PEA system, design and development of PEA system, experimental investigations on space charge, analytical model of space charge formation in polymers, conclusions and future scope of work for you if any one of you are interested to go in that direction. So this is a well-known break-even point known in the literature for AC and DC transmission. So beyond certain kilometers, actually DC is better than AC. Okay, so but unfortunately in India or over the world, the number of DC lines are less compared to AC, or percentage of DC is less compared to AC, right? Now among DC also, transmission through cables is gaining momentum due to the reason that, see, it minimizes the land requirement actually. So there are lot of social movements against taking land by governments, etc. Even now some issue is going on. So that kind of social problems, right of way problems, people have right of way, they want to move freely without any obstruction, like transmission line, tower, or through without getting exposed to the magnetic field of transmission lines. So transmission through cables is gaining momentum. So and increasingly, even in metro lines or even in cities, so we are forced to have cable transmission there. So, but what are the problems with cable that are very interesting and need to be addressed now. So this is one more thing, one more advantage. For example, power grid A and power grid B, if they are need to be connected, if there is a link like DC, that will always be advantageous. There you need not have same frequencies. So this kind of problems occur in European countries where frequency of one country is different from frequency of other country. Also, even in one system like a big Indian system, so the northern grid or southern grid, these may not be operating exactly at same frequency. Though the frequency is 50 Hz, it need not be 50 Hz, maybe 51 Hz or 49 Hz, like that. So if the two power systems are connected through cable transmission, which is DC, then there will be more scope for more improvement in the stability of a system. So that is why power cables, and in the power cables, HVDC is gaining importance. But what are the problems? Cable, unlike overhead line is suspended in air. Even if breakdown occurs or flashover occurs, it can regain the strength and it can be continued to be used. But unlike that, cable, if it fails, you have to replace. There is no other way. So solid insulation, it is because of the failure of the solid insulation. Once it fails, that's all, failure only. So that is why ensuring reliability of cable transmission is very, very important. So cable should not fail for 25 to 30 years once it is laid down. Otherwise you have to dig it, open it. First of all, to find the fault where it occurred. So you have to dig entire the line, or even if you have, nowadays you have false locators also, but they also cannot locate exactly at the location of the point. You have certain minimum distance, you have to dig it out and then verify where the fault has occurred. So there are some limitations. To avoid these problems, you need to ensure high reliability by using good insulation, which will give the lifetime of the cable without failure until 25 to 30 years. Before that, if it fails before say 5 to 10 years, then it is not economical to go for cable transmission. So among the insulation that is used for HVDC cables, so these three types are very prominent. Oil impregnated insulation. Oil impregnated insulation means what? So the cable conductor is surrounded by paper. The paper is impregnated with oil or kept in oil under pressure for some time, and that paper is called oil, that insulation is called oil impregnated insulation. Second thing is oil filled insulation. In oil filled insulation, this entire cable with outer insulation, this paper insulation only will be used, but this will be kept in a tube in which oil is filled, and that oil is maintained at a high pressure. So the purpose of using oil, a tube, and then filling the oil in it and then using the pressure is to minimize or is to eliminate the voids. When you keep oil under pressure, so it percolates into the paper insulation. And the third one is polymer insulation, right? Now these two, oil impregnated and oil filled insulation, these two have voltage limitations. We cannot go beyond certain voltage, as well as length limitation. So the reason is here, we have to keep the oil under pressure in a tube. So obviously the distance is limited, otherwise you should have frequently some equipment which will maintain the pressure of the oil. And one more disadvantage with such cables is, if you use in submarine, if you use them as submarine cables, so in case of cable failure, when you cut and open, oil will flow into the sea and it will contaminate the sea. Not only that, water will enter into the pipes. So there will be lot of difficulty in case of failure of a cable, oil filled insulation cable. So due to these disadvantages, also the temperature to which the cable can withstand for this oil filled and oil impregnated insulation is just about 60 degrees centigrade. So it's also a limitation. When temperature is limited, means what? The current rating of the cable will be very small. So due to these limitations and ease of use of polymer insulation like low density polyethylene LDPE or cross linked polyethylene, etc. So the polymer insulation is gaining momentum. So almost all AC cables now are replaced by polymer insulation only. You will find some solid insulation, white color insulation surrounded by some black coating, that is semicon coating, which is the outside of the insulation is semicon coating, which is again a conductor, used as a conductor. Now polymer insulation is successfully being used for AC. For DC also, until 250 kilovolts already people have used it, and for 350 and above research is going on. So this was one of the cable link in Japan between Hokkaido. Hokkaido is the northern part of the Japan. It is almost covered by ice. So there is little scope for power stations there. So in the mainland Japan, the middle portion, in the mainland Japan only lot of power stations are there. From this mainland, the power will be supplied to the island, Hokkaido Hokkaido, the northern part, and this is called Honshu, right. So similar connections are there in entire European region also. You can see the world map, almost always many islands will be surrounded by each country. So current will be, power will be produced in mainland only, and it will be transmitted to these islands using power cables. So that is why there HVDC cables are normally used. In our country also, from India to Sri Lanka, there is a plan for building 450 kilovolt HVDC link, and even for Andaman also we are thinking to implement this one. So now also sometimes we will have some power source in islands, and that can be used in mainlands. Okay, so that is also possible. So if the length is very long, AC cable cannot be used. So why AC cable cannot be used? Cable is actually a cylindrical capacitor, right. So if the length is increasing, the capacitance will be increasing. Then if under AC, it will consume lot of reactive power. Okay, so the reactive current will exceed rated current at around 80 kilometers of a typical AC cable. So if it exceeds the rated current, then the cable cannot be used for any active power supply. So that is why AC cables, there is a limitation of power transmission on length of the cable. So if the length is very long, then obviously you must go for DC cable transmission only. For example, to connect India to Andaman, mainland India to Andaman Nicobar Islands, the distance is more than 80 kilometers. You cannot go for overhead transmission at all. It is ruled out. So you have to go for cable transmission only. In that, AC cables also you cannot use because it exceeds the rated current after 80 kilometers. So the reactive current exceeds the rated current after 80 kilometers. So you cannot use AC cables also. So that is why the only option is HVDC cables. So during 1970s, they have replaced the insulation for 250 kilovolt line. Replaced the insulation in the sense, earlier they were using oil paper insulation, oil filled insulation rather, and that cable has got damaged. Then the Japanese government decided to use polymer insulation, because at that time already polymer insulation has been used for AC cables. So they have implemented the polymer insulation to this DC also. See, actually the dielectric breakdown strength, if you conduct breakdown strength normally, DC breakdown strength will be very high, roughly 2 to 5 times higher than AC breakdown strength. But still this cable failed. Though the polymer insulation is used, whose breakdown strength is very high compared to AC, but still this cable failed. AC, it was never failed, it was successful. Not only this, over the world several cables failed after 1970. Whoever, the power companies, whoever gone for polymer insulation, the cables failed. So the reason was not known. So at that time people have cut it and then cut the cables which failed, and then some charged powder they have thrown and then thrown on the surface and have estimated the electric field, etc. And they, interestingly, they found that within the insulation, this charged powder has got stuck on the main insulation portion of the cable. Actually, ideally we do not expect charges inside the insulation. So the charged powder which gets stuck to the insulation, what does it mean? It means that some other opposite charge is there on the surface of the cable, cross section of the cable. So it means that some charges are being formed inside the insulation. So that was the first observation, where dielectrics can also have some charged traps, some trapped charges inside them. Okay, ideal dielectrics we have been studying is, inside there will be no charge, but at interfaces we will have charges. Okay, so now this charge which is present inside the space of the insulation, that is called space charge in the literature. So this was suspected to be the main reason for the failure of the cables. But space charge, how it forms, later people have investigated. So when a dielectric material is subjected to some electric field, so dipoles inside tend to rotate or tend to align in the direction of the electric field, and ions migrate. See, for example, ions from negative ions will tend to attract the positive interfacial charge, and positive ions tend to get attracted to the negative interfacial charge. This plus 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 minus minus minus, why this is accumulated here? This is due to the alignment of dipoles in the direction of electric field, and these charges are called interfacial charges. This actually neutral only. This is ideal dielectric. Okay, so these are so close that you will not feel any effect of these inside, and the net charge you may consider it as 0 only. But these interfacial charges are formed ideally, but when practical insulation is there, if there are some ions inside the insulating materials, they tend to get attracted like this in the opposite. So in this case, what you observe is, at the interface you will have positive charge, immediately that you will observe some negative charge, but these have been observed to be never combining with each other. And here also plus and minus charges. So such kind of charges where interfacial charge is different from charge just within the insulation is known as heterocharge formation in the literature. And similarly, charges are injected in another case. So charges are injected from the surface of these two little bit inside the insulation like this. In this case, same charges are being injected. So this kind of phenomena is known as homocharge formation in the dielectrics. So these two types of special charge formation is observed. Apart from this, one more type is observed, that I will tell you later. Now what will happen if charges are formed inside the dielectric? See, if there are no charges inside the dielectric, only interfacial charges are there, in that case inside the dielectric, the electric field will be uniform. If this is thickness 0 D, D is the thickness of the insulation, electric field will be simply V by D, voltage V applied by divided by D is the distance. That is the uniform electric field, we can say. But when the charges are formed like this, for example heterocharge injection like this, so this is the kind of electric field you will observe. Why such kind of electric field you will observe? So 1 by epsilon integral charge, integral rho dx will give you the electric field. This is using Poisson's law, you can obtain this equation. So integration of space charge will give you the electric field. So when the charges are like this, so whenever negative charges are like this, so to compensate for, more positive charges are formed at the dielectric interface. Due to that, your electric field will be enhanced like this at the edges, and it will come down like this. Why it will come down in the inside the insulation? See, we are considering the case of some constant voltage application. For comparison, you have to apply same voltage. So when V voltage is applied, if there are no space charges within the insulation, electric field is simply equal to V by D, uniform across the insulation, right? But when charges are formed, at the edges, you see, in this case heterocharge injection case, at the edges the electric field is high, but E dot dr, or area under the electric field, will give you the voltage. E dot integral E dot dr will give you the voltage. So voltage is constant here. So when voltage is constant, if it is more at the edges, it must decrease in the center. Okay. So the total area of this must be equal to total area of this, because same voltage is applied. So similarly, this is heterocharge injection case, and similarly when homocharge is injected like this, same charge is injected like this. In this case, at the edges it will be low, slowly increasing, and in the middle it will increase. So in either case, what is observed here is, in case of no space charge, the electric field is constant and it never crosses the average voltage, E is equal to V by D. But in the case of charge formation, whether it is hetero or homo charge formation, always the maximum electric field is more than the average value. This is E is equal to V by D, for reference I have drawn here. Okay. So this is the maximum field, and in this case this is the maximum field, either in the middle or somewhere in the insulation. Whenever there is some charge formation in the dielectrics, always there will be electric field enhancement. Enhancement in the sense it is more than the average value of the electric field. So what does it mean? You will be applying same voltage to an AC case and DC case also. AC case, it will be uniform in a sheet sample, but in DC case it will be non-uniform, and that non-uniformity is occurring due to charge formation. In AC, such kind of charge formation is not observed, because AC means alternating, the voltage will be alternating. So movement of charge is restricted. Half cycle it is positive, half cycle it is negative. Okay, that is why the net movement of the charge is restricted, it will be only oscillating. That is why under AC, space charges are not formed or rarely formed due to some other reason. So this is the effect. Electric field enhancement will be there inside the insulation. When higher electric field is there, then it causes breakdown or it causes aging, several effects will be there. So these are the possible effects of electric field distortion or enhancement by space charge. Local electric field overstressing in the insulation, somewhere at the edge or somewhere in the middle, the voltage, the electric field is very high. So this is what is known as local enhancement. So this local enhancement may result in the breakdown of insulation. There the breakdown may be initiated due to high electric stress. And second, local aging effects. So wherever the electric field is high, there the aging is accelerated, So there the more aging can occur. So life of insulation may also become reduced, and may aid leakage or conduction current of the insulation. So whenever electric field is high, J is sigma E. So if it is its conductivity is sigma, so sigma times E. So if E is high somewhere, there the leakage conduction may be very high, and that may cause failure of the insulation, damage of the insulation. And we don't know, continued presence of space charges may cause some unknown effects. Until now the investigations are not complete. So some unknown effects may also happen due to the presence of space charges. So these are all the reasons why measuring space charge and knowing space charge inside the dielectrics, and from that estimation of electric field is very, very important, considered very important. Now space charge measurement technology, in that electric field is spatially and temporally non-uniform inside the insulation, that we have seen just now. So one has to see through the insulation. So one way is to the destructive way, just cut the insulation and use some charged colored powder. So for example, positive charges, you use some red color powder. So that powder you ionize it so that it attracts to positive charges, and for negative charges you use some blue color powder, and that attracts to that may be ionized such that it attracts to negative charge, and spray on the insulation which will attract, and from that color you will find. Actually this powder you can obtain from that printer toner. Actually printer toner, the colors you are getting, 3 colors will be there, no? So these three colors are ionized, actually ionized powder only. So these 3 powder we have actually done the experiment. If you spray, it will attract, and from that you will know. But the problem here is when you are cutting using a metal knife, that knife is a conductor and it damages the charge, it discharges the charges already present in the insulation, right? So that is the one of the problems of using this destructive method, and you have to distract or you have to damage the insulation, right? It is not always a preferable choice. Second is non-destructive way of measurement. So how to measure space charge which is inside some insulation by using some tool from outside. So this is very interesting actually. So measurement without altering original charge profile, and that tool should not change the charge profile whatever is existing, and also have good accuracy. So these are all some issues how to proceed with the measurement of this one. So these are the basic investigations we have planned in our research lab. So research on measurement method, and that after identifying some measurement method, modeling and simulation, and design and development of the method. That's what we have used. Pulsed electroacoustic method for measurement of space charges. So after that, development of 3-terminal electrodes set up for leakage current measurement also. Now these charges formed inside the dielectric, and these charges inside the dielectric and external leakage current is somewhat related, what we suspect. So if we could measure, we can measure leakage current, and from that current, leakage current measurement is very easy compared to space charge measurement. So if we can measure leakage current, and from that if we can guess what the type of space charge and how the charges are trapped inside the insulation, that will be of greater use. So with that purpose, we have also developed some 3-terminal electrode for measurement of leakage current. That is well known, that 3-terminal electrode for measurement of leakage current is well known in the high voltage engineering. Now after doing this, what is the space charge phenomenon, how it is occurring, and we have also observed some charge packet formation, in which what is happening is suddenly from anode side or some that positive electrode side, suddenly a charge packet is emerging and passing through the insulation and reaching the opposite, but is never merging with the opposite electrode. So this kind of phenomenon is known as charge packet formation, and it happens in LDPE about 100 kilovolt per millimeter, above 100 kilovolt per millimeter field strength. So this we want to investigate. So this is the pulsed electroacoustic measurement method. So here I will explain you. So this is the system. There is a electrode, top electrode, and here some backing material is there which is also conducting, and this is the dielectric specimen in which we are measuring the space charges, and this is the ground electrode. So here these two are electrodes. Actually this material is also conducting. So the entire this up to this you may consider it as electrodes. Between these two electrodes this dielectric specimen is placed. And below that a PVDF sensor is placed, and again some backing material and some electrode is given here. So the principle here is acoustic principle. Acoustic principle means sound wave. So the sound wave, we will generate a sound wave here which is proportional to the space charge, and that part of the sound wave actually whenever it is generated it will move in either direction. Okay, so that part of the sound wave which reaches this PVDF sensor, piezoelectric sensor, that converts sound into electricity or acoustic signal into electricity, so or electrical voltage. So that voltage we will tap and that will be amplified and measured. So here you can see, but how to obtain this? So when the top electrode is supplied with some DC voltage and this electrode, this ground electrode is grounded, it means that certain voltage is applied to this dielectric specimen. So with this voltage application, charges will be formed inside the insulation. If it is for example say LDPE insulation, low density polyethylene. Now these charges need to be measured, or an acoustic signal proportional to these charges should be generated. Now here we have made an arrangement here. This is the voltage source. Through a resistor we are applying the voltage. So this is taking care of our DC voltage application, right? Now to measure that, this circuit, high voltage pulse circuit is used. Here we used a capacitor and used some pulse source here. So what will happen with this arrangement? The capacitor will block, for DC voltages capacitor will block. So it will be fully charged to this DC voltage and no voltage can transmit this way. But whenever a pulse appears, the capacitor acts as a short circuit for any high frequency signal. So that is why this signal will be superimposed on this DC. So ultimately you will get your DC will be there and this pulse will be superimposed on that DC voltage. Then what will happen if a short duration pulse is applied to some insulation specimen? So naturally some force will be generated, will be acting on the charges due to this short duration pulse. Okay, so it will cause slight disturbance, slight movement, a jerk proportional to the pulse whatever we have applied. So that jerk causes an acoustic wave or sound wave. Sound wave means pressure wave. So this pressure wave which is generated due to this pulse voltage, and your technique, this technique also depends on the width of the pulse. It should be in nanosecond range only, it should not be more than that. So we have used 3 nanosecond pulse of 600 volts. So that will cause some disturbance, and then that acoustic wave will reach this PVDF sensor, and this will be amplified and then fed to an oscilloscope, and from there we will take the data and measure it. So this is the diagram that is explaining the acoustic wave movement in the insulation. So this technique is developed by some Japanese people, but it was very costly to purchase that one, right? And that and we also felt that the voltage they are supplying, the voltage rating of the equipment they are supplying is just 10 kilovolts, and we cannot exceed 100 kilovolt per mm by using very few micron level thickness samples. And even if you use 1 mm sample, the maximum field that we can apply is 10 kilovolt per mm only. So we cannot see any phenomenon. Actually the rated voltage of LDPE is 20 kilovolt per mm now, and it is bound to increase. Now people are trying to increase. So that's why what we thought of developing our own system at our institute. So for that purpose, we have searched the literature that nowhere the modeling of this system has been done. So what we first did is we have modeled the PEA system as such, how the each part and how each part is reacting, and how the various acoustic signals are moving within the insulation, and how the reflections, whenever acoustic signal is used, as usual you have seen in the previous slide. So acoustic signal, whenever it reaches some interface, it will get reflected back, and here again interface. See this backing material, why it is colored with the same as this insulation sample is. The backing material is nothing but the insulation sample only. In that, what we have done is we have used some carbon particles to make it conductive, make it a conductor. So this is insulation, this is conducting, but basically the base material is same. In this only some carbon particles are used to make it conductive. The purpose is, whenever some acoustic signal is generated, we don't want it to get it reflected here. It should travel some distance and get it reflected. Okay. The purpose is, if it gets reflected here itself, then it merge with the original signal, and the signal whatever we are obtaining at the PVDF sensor is not the actual signal. So that is why we use some backing material here, and after so when the signal transmits like this, it will get reflected here also, but that will go. So what is the thickness of this ground electrode? That is very important. Otherwise what will happen, here the acoustic signal slowly moves here, and here it gets reflected, and it comes back again, it comes back like this, a part of the signal will be transmitted, so like that. So to avoid that problem, we need at least a certain thickness of this insulation, that I will come back to that one. Now here the PVDF sensor, below that also some backing material is used. Now in this case, this PVDF, this is also PVDF material, but some carbon particles are included to make it conductive and to avoid reflection at this interface. Due to several reasons, we thought of modeling and simulation of this PEA system. And the modeling, as you can see, we have two parts actually. One is electrical part. In electrical part, what we are doing, one DC source is supplying voltage to some dielectric specimen, and above that we are superimposing some pulse voltage. So that contributes to electrical part. Here this is the DC source through some resistor is coupled to, this is the sample. Sample can be modeled as capacitor in parallel with resistor like this, several capacitors, small capacitors and resistors in parallel. So this is your DC source, and here this is the pulse source. Normally pulse source will be supplied through some cable. This pulse source normally is supplied through a cable. Cable is again a transmission line, So the pulse voltage gets transmitted like on a transmission line, and this is very high frequency signal. So you have to model it like a transmission line with Z0 40 ohms like that. So this is modeled in PSpice actually. So now once the signal reaches here, it should not get reflected back. That is why we should use some terminating circuit there, and then this coupling capacitor through which that high frequency signal passes here, and this coupling capacitor also blocks this DC voltage this side, right? So this is the electrical circuit simulation, electrical part of the circuit. But this electrical part of the circuit will generate an acoustic signal. That acoustic signal also has some acoustic circuit. what we modeled in PSpice. So this is the second part of the circuit, you know. So acoustic circuit also we have modeled it as an electrical circuit, just like a transmission system. So you see, this is upper electrode, this is backing material, and interfacial region, interfacial charge is modeled as a voltage source here, and this is sample, and again interfacial acoustic force, this is ground electrode, and here the transducer, and then amplifier, and then backing material, then aluminum electrode. So all those parts, each part will be is modeled as a transmission line. But here in the part of acoustic signal, the pressure signal whichever is moving down corresponds to our current in electrical signal. So this is modeled, and each of the parameters, the characteristic impedance Z0, Z1, Z2, Z3, etc. we have found, and we have simulated the acoustic circuit also. So we have found exactly what we actually get in a PEA system in experimental setup. So this is the thing. See, if you this is for 250, A is for 250 microns, and B is for 500 microns. Effect of thickness of ground electrode, right? So here you can see this is false value. Actually these two are, this is ground, this is the signal at ground electrode, this is the signal at x is equal to d. So बीच में जो ये जो आया, this is not actually the phase charge. So it is very, very important to understand the system, otherwise you may misinterpret. And there are several reflections you can see here. So when you make a PEA system and measure the charge, and you are getting a signal like this, so you don't know whether this is ground electrode or this is ground electrode, this is high voltage electrode, all this is space charge within the insulation. You do not know. So that is why simulation is very important now. So for example, even if you consider this is the ground electrode, and this is, because this is first negative peak and this is first positive peak, so this is cathode, this is anode bolke, you may think. But in that case you may think that, oh, this kind of charge is formed within the insulation, but it is incorrect. This is a false value or a reflection actually. Okay, so if the thickness of the ground electrode is not sufficient, a reflection will come and join there. So actual signal, if when you use 500 micron thickness, so this is clear now, there is no charge within these two peaks, right? So this is actually up to this is the space charge, you can conclude. But how you concluded, you know, in simulation everything is possible. You may assume interfacial charge only at one electrode and then simulate the results. So then see which is reflected, which is actual, which is like that. So we have done that actually. So I will show you first that one. So you can see, so only sigma d we have simulated, and how frequently we will get that back due to reflections, and only sigma naught also we have simulated, and clearly this is due to ground electrode, this is due to top electrode, right? So clearly between these two, if you superimpose this one, between these two space charge should be there. So reflections, these are all reflections of this peak only. So like that we came to an understanding of the signal, right? So these are all the simulation results for different effects of different. See, for example, this is due to differences in pulse voltage whatever we are applying, that is probing voltage. So if probing voltage, though it is 3 nanoseconds, it may have some overshoot like this, it may have some further overshoot like this, and that may cause different types of charge profiles. So like this, for example, this is smooth, this is due to this one, and due to this one this type of waveform is obtained. It doesn't mean that this is the actually space charge, it happened due to your probing pulse. So probing pulse, the sharpness of probing pulse and the the shape of the probing pulse is also very important in estimating the space charge, right. So this is the effect of PVDF transducer we have found here, and similarly effect of backing material also. When you use different kinds, see backing material, if it is not perfectly matching, see just like impedance matching, I think you are aware of impedance matching. So when a wave, a transmitted wave reaches at its end point where if it finds same impedance as the transmission line, transmission line's surge impedance, there will be no reflection. But if it is different, say Z0 by 2 or 0.7 Z0 or 0.9 Z0, in that case some portion gets reflected and some portion gets transmitted like that. Here if your backing material is not perfect, you will always find some reflections which will occur, see here, due to false value due to reflection from the lower backing material. So like that several investigations we have made, and finally we could make one good PEA system. So this is the effect of amplifier input response. See amplifier, you see every system also has some transfer function, you know. So even though you are applying some probing pulse which is very sharp, ideal, and it is very impulse in nature, so the generated acoustic wave is also fine, phase charge within the insulation, but as it is transmitting through various say materials and finally reaching the transducer, and from transducer it is amplified using an amplifier, this amplifier has its own response, it's certain bandwidth only it can transmit. So it has certain transfer function that is affecting the original signal. Actually we will get like this, like these peaks, you know, but this is after the, so this is here the electrode ends. So outside the electrode you are getting like this. People thought like that. So this may be something else. So finally they could understand that that is due to the effect of amplifier. So amplifier's impulse response is causing some distortion in the results. So or the original signal is getting convolved with the amplifier's impulse response. So what we need to do is we need to deconvolve the signal and obtain the original signal. Deconvolve means in frequency domain you have to divide it by the transfer function to obtain the original signal. So this is how actually original signal will be there. This is actually reaching the transducer, and this is after the amplifier that we have found in our simulation also. So here see, this is the actual signal that is reaching, this is actually the generated signal, and this is reaching the transducer. You can see after the transducer you can clearly see this type of shape distortion here. So this supports the already found result that amplifier distorts the result, space charge result, and we have found the transfer function of that amplifier also, and then obtained the original signal that is obtained after the simulation. So this is the electrode setup that has been developed at our institute. Block diagram is shown here. This is the pulse voltage, resistor and capacitor, and here the high voltage electrode, and this is the high voltage input, and this is aluminum electrode, and below this PVDF sensor and backing material. Here the amplifier is connected and amplified the output signal is obtained. So this shows our experimental setup in our lab actually. So the signal is fed to this oscilloscope, and from there we obtain. This is electrometer which will be used for measuring the leakage current. So these are also experimental setups, and this is the 3-terminal electrode. So we have made very robust 3-terminal electrode here using some spring arrangement and some flat electrode with guard electrode and all, and we can place the sample and we can put either oil or gas, SF6 gas inside the chamber and then measure the leakage currents. So this is the experimentally obtained signal from the oscilloscope. This is for 100 micron sample, this is for 200 microns low density polyethylene sample. Here you can see clearly this peak is at ground electrode, this peak is at high voltage electrode. As I have already told, you have seen like this, you see like this, no? But this is actually not the space charge, it is due to amplifier response. Now we have experimentally found the amplifier transfer function and deconvolved it and seen that it is exactly flat. So this is the same charge profile at different times after voltage application, how it is moving and all we have given here. Actually this charge plots, this color plots will give you clear understanding. Here this is the time axis, with the time how it is, how the charge is moving or charge is changing, voltage, same voltage is applied, we have not disturbed anything. So this is the thickness, please don't talk, whoever is talking, please don't. So this is the thickness, and this 0 is for ground electrode, this 100 is for high voltage electrode. So here the color is difference, means the charge is negative here, and red color means charge is positive here. This is minus 300 to 200 you can see. Now you can see here some charge is coming like this and getting accumulated here, and this is 0 to 10 minutes, 10 to 20 minutes. Actually we cannot plot continuously due to the limitation of software. So this is continuous only with RAM. Up to 30 minutes we have done the experiment. You can see this charge is accumulating just adjacent to this electrode, but it is not merging with this even after 30 minutes also. And here different kinds of charge formation you can see. Here positive charge and negative charge and positive charge, like this. So different kinds of phase charges for different, this is for A 100 kilovolt per mm, B 110 kilovolts per mm, etc. I am sorry, we have increased the voltage actually 100, 110, but the time is continuous. So corresponding electric fields we have plotted, as I told you, otherwise that must be uniform, right? So this is a negative electric field actually. So ideally it should be uniform like this, but you can see clearly how distorted it is inside the insulation. So this peak voltage is around 150 kilovolt per mm, average may be around 100 kilovolt per mm. So that much enhancement in electric field is observed. This is field enhancement factor. This is the different electric field plots, the space charge plots and corresponding electric field plots. And this is field enhancement factor. Field enhancement factor is defined as maximum field divided by average field. It is very important consideration for insulation, right? If field enhancement factor is high, then the insulation is not good for application. So with the time also we have plotted this, and for leakage current measurement we have very good accurate DC source. We have imported this from Japan. See, we have applied electric field in steps with time like this, and we have measured the leakage currents. So that plot shows until 60 minutes the leakage current at different voltage levels. We started from 100 kilovolts per mm, 110, 120, 140 like this, and similarly we have done the test. This is the previous test is for just 30 minutes. This test for 30 hours we have conducted the test. You see clearly even after 30 hours also the leakage current is not getting saturated. So it is very, very important consideration, because normally in other insulation other than polymer insulation it saturates within few hours, right? But low density polyethylene is very good insulation, it has high breakdown strength, and it can be easily manufactured, and cables or whatever shape you can make very easily. This is plastic, so that's why it has some advantage than paper. How paper insulation is to be made? You have to wrap it around. Think about wrapping and think about manufacturing with some plastic accumulating on a cable, extruded process. So that is very simple and easy to manufacture and easy to replace also, easy to transport also, weight is also less, right? But paper insulation you have to wrap it using some machines, and it is a cumbersome process. So that's why LDPE has highest breakdown strength and has also several advantages, but see, it is not getting saturated even after 25 years. Think about some 20-30 years then. We don't know what will happen. It may be continuously degrading or something happening, and then after 2-3 years or 4-5 years, what will happen to the insulation is not known, right? So this is the important consideration. Ultimately, what matters is long-term performance. Initial performance may be better, but over a long run, whether the insulation will perform the same, give the same performance or not is a question. So that's why people have come up with mixing LDPE with some nano powders, nano MgO, etc. So then it has been observed that the electrical field strength, electrical breakdown strength and long-term performance, of course they have conducted for 30 days or so, because we can't afford to conduct an experiment over a period of 5 years, 5 years, 10 years. For the life of the cable itself is 30 years. 5 years is some, how much percentage is? Some 100/6, some 20% of the time we can't afford to keep for experimenting itself. So that is why 30 days, up to 30 days they have conducted and seen MgO particles mixed in LDPE are giving better performance and long-term performance, and space charge is interestingly absent in that. Even 100-200 kilovolts you go, kilovolts per mm you go, there is no space charge observed. So conclusions: some charge packets emerge from electrodes under sudden high electric field applications. Long-term charge measurements indicate no pocket charge movement. So short period, I have not told this in the presentation, but short period application of voltage, very sudden application of voltage is leading to charge pulses, charge pockets emerging from the electrodes. But when you conduct the experiment for 5 hours, the 30 hours experiment, in that we did not observe actually. So only for few minutes the charge accumulation took place, and after that it stabilized and there was no problem. So whether the space charge will actually cause a problem in the long term is not easy a question actually. So but still the investigations are going on. So right now I don't want to make a final conclusion on that this is it. Okay. So leakage currents also did not saturate even after 25 hours. Now we are planning for more than that. See, several days we want to conduct and then see the experiment, see the results. And there is a need to understand all above phenomena, in the sense there are several scopes here for your research, if you are one of you are interested or many of you are interested. For example, charge packets are emerging from the electrodes and reaching the opposite electrode. So you can model this by modeling the sigma, but you need to cover certain literature, background survey, and then understand the problem to make a problem and do research on it. So it can be a PhD thesis also. I am telling you that much scope is possible here. And other than modeling, you can also improve the existing materials. For example, if somebody is interested in nano related things, so you can use some nano powders and mix them in some insulation, say epoxy resin or other materials, polymeric materials, and then find out their characteristics or improvement or scope of improvement, etc., by studying their space charge or leakage current, etc. So, and several related problems also you can form here. Even the method of space charge measurement also you can consider. There are still improvements are possible. We have developed up to 40 kilovolts. Now there is a scope for developing it for 100 kilovolts also, using some modified electrodes, etc. So that's also possible for you. So there are some there can be some MTech projects also based on this work. If you are interested, you may contact me, no problem, I can help you if you are very much interested. Thank you for your attention.
Thank you so much.
Thank you.